Hello everyone, this is the next lecture of the subject Special Electrical Machines. Myself Dr. Vani Bhargava, and in this lecture I am going to start the second unit, and in second unit we are going to cover the stepper motor. So what are these stepper motors? Stepper motor is a special electrical machine which rotates in discrete angular steps in response to a programmed sequence of the input electrical pulses. It is also known as a step motor or the stepping motor. It works upon the principle of magnetic interaction between stator and rotor, as a result of which the rotor moves. The stator of this particular machine has windings, but there is no winding over the rotating part of the machine. Rotor is a salient structure without any winding. The rotor may or may not have the permanent magnets over it. So, it may have permanent magnet, making the machine a permanent magnet stepper motor. It may not have the permanent magnet, simply the soft iron rotor without any permanent magnets, without any windings, and thus making the machine a variable reluctance stepper motor. The robustness and reliability of stepper motor makes it very popular in the control applications. There are some more salient points of the stepper motor. The input and output relation is direct and rigid, and it is possible to have an open loop control system, that is without any feedback sensors, unlike the servo motor. So, stepper motors with good precision can very well be employed in open loop control system without utilizing any sensors for the feedback loop. Applications of these motors are diverse and they range from a small wristwatch to the artificial satellites. You can see the range of application. The applications may be in these small wristwatches, or they also find the application in artificial satellites. These motors are available with a power range of 1 watt to 2.5 kilowatt. Just see the range of power in which these motors are available. 1 watt to 2.5 kilowatt. And the torque range in which these machines operate are 1 micronewton meter to 40 newton meter. So from here you can have an idea of the diverse range for which the motor can well be employed. Let us start with the construction, general operation, then types of stepper motor. So starting with the basic construction of stepper motors. As I told you, a stepper motor is an electromechanical device that converts electrical pulses into discrete mechanical movements. It divides a full rotation into a number of equal steps, which makes it ideal for applications which require precise positioning and control. For example, CNC machines, robotic applications, printers, and in industrial automation. The basic constructional details of the stepper motor are as follows. It consists of a stator, a rotor, bearings of course, shaft, and cover, and the housing. This is the basic structure of any electromechanical energy conversion device. I mean to say any electromechanical electrical machine. Constructional features further. The stator is the stationary part of the motor and it contains a set of windings or coils which are arranged in a circular pattern. The stator windings are housed in stator slots. These stator slots are evenly distributed along the inner circumference of the motor housing. Let me draw it for more clarity. The stator is a hollow cylinder like this, and slots are mounted. Just ignore this part here. So these are the slots over the, they are of course equi-width, equidistant slots over the inner periphery of the stator cylinder, right? There are some more details. I have placed those details in the coming slide. The types of stator slots are, they may have the open slots, semi-closed slots and the completely closed slots. All of them are having particular advantages and disadvantages, and we have to choose the type of slot depending upon the requirement of the application. These windings which are placed in the stator slots are energized in a specific sequence to generate a magnetic field. When electrical current passes through the windings, they create a magnetic field, and this magnetic field interacts with the rotor, causing it to take a step, which is movement by some predefined angle depending upon the energization of the stator winding. The number of windings and their arrangement determines the number of steps per revolution. The stator pole formation takes place around the inner circumference of the motor housing. These are some more details about the stator slots, the open stator slots, the semi-closed stator slots and completely closed stator slots. Moving ahead with the construction, let us talk about the rotor. The rotor is the rotating part of the motor and is positioned inside the stator. So, inside the hollow stator cylinder lies the rotor. The rotor can be made of permanent magnets. It can be made of soft iron or laminated steel core, or it may possess the hybrid construction. So accordingly, we are having permanent magnet stepper motors. Soft iron or laminated steel core rotors are used in variable reluctance stepper motor. So we are having permanent magnet stepper motor, we are having variable reluctance stepper motor, and we are having hybrid construction which employs the features of both permanent magnets as well as variable reluctance type construction. The rotor of the machine aligns itself with the magnetic field generated by the stator winding, and in aligning itself with the magnetic field generated by stator winding, actually rotor develops a torque over it and finds a position of rest depending upon the position of the magnetic field produced by the stator winding currents. The other parts of the construction are, there are bearings. Bearings are mounted on the rotor shaft to support smooth and precise rotation. They reduce friction and provide the mechanical support. So, shaft actually rotates between the bearings. Shaft is attached to the rotor. It transmits the rotational motion of the rotor to the load or whatever external mechanism is there, which is there to receive the rotor movement. End covers and housing. So, the stepper motor is enclosed within a housing that protects the internal components from the outside environment, and this hollow cylinder, which is basically the housing of the motor, is actually covered with the help of end rings at the both ends of this hollow stator housing cover. Types of stepper motor. As I told you earlier, depending upon the type of rotor construction, stepper motors are of three types. Permanent magnet stepper motor, then we are having variable reluctance stepper motor, and then we are having hybrid stepper motors. So let us just have a glimpse of all these type of motors. In permanent magnet stepper motor, the rotor is made up of the permanent magnets, right? The stator has windings that are energized in a particular sequence to create a rotating magnetic field system, What is the meaning of rotating magnetic field system? It would be more clear when we will go deep inside the operation of each type of machine. To create a system in which magnetic field is rotating, actually the rotor phases are energized in sequence. So for example, phase A is energized first, so the magnetic field would be produced by the phase A and it would be at a certain position in the space. Now phase A is de-energized and phase B is energized, so the new position of the magnetic pole so created would be somewhere else. In this way, in a particular fashion, we are going to vary the rotation, we are going to change the position of the rotor, which is actually following the resultant magnetic field after energization of a particular or more number of stator phases. So basically after energization of the stator phases. In all these machines, the rotor aligns with the magnetic field generated by the stator. How the rotor is aligning, what force is acting depends upon the type of rotor. So if we are having permanent magnet stepper motor, so force of attraction and force of repulsion between the magnetic fields, between the magnetic poles is there, which causes the rotation of the rotor. The advantage of permanent magnet motor is high torque at low speeds and a good holding torque. Holding torque is the torque which acts over the rotor in its position of rest, or it can be said as the torque that holds the position of the rotor in its position of rest. The disadvantage of such machines is lower step resolution. We will discuss in detail when we will go into details of the permanent magnet stepper motor. The basic construction, its stator contains multiple windings placed in a particular way, placed in a particular manner. The rotor contains radially magnetized permanent magnets. One thing which is important over here is the step angle. The step angle is approximately 7.5 degree to 15 degree per step. Now let us move to variable reluctance stepper motor general construction. They are also said to be the VR stepper motors. The rotor is made of soft iron or the laminated steel and has multiple teeths. See, there is no winding over the rotor, there are no magnets over the rotor. The stator has windings that are energized sequentially depending upon what kind of rotation, what step size of rotation is required, what direction of rotation is required. The rotor aligns with the lowest reluctance path. Lowest reluctance path is the path of minimum magnetic resistance. They possess the advantage of simple construction and low cost, but at the same time, the disadvantages are there, and the disadvantages are low torque and the lower precision as compared to permanent magnet stepper motor. The basic construction is stator is made up of the laminated steel and contains multiple windings. Rotor has teeth and no permanent magnet, and the typical step angle size may vary from 5 degree to 15 degree per step. Then comes the hybrid stepper motor. The hybrid stepper motor combines the features of both permanent magnet and variable reluctance motors. The rotor consists of a cylindrical permanent magnet with toothed soft iron caps on both the ends. The teeth of rotor align with the magnetic field of the stator. This motor actually combines the features or advantages of both permanent magnet and the variable reluctance motor. They possess the advantage of having higher torque, better precision, and smaller step angles are possible over here. But at the same time, the disadvantages are they are expensive and more complex in construction as well as operation. The basic construction: stator has multiple windings and the poles are created accordingly. Rotor has permanent magnets and toothed soft iron caps. The step angle range may vary from 1.8 degree to 3.6 degree per step. The general working principle of stepper motors. The stator windings are energized in a specific sequence. The magnetic field generated by stator attracts the rotor teeth. In case of the variable reluctance and hybrid machine, and or it aligns with the permanent magnet poles if the rotor is of permanent magnet type. The rotor moves step by step as the stator windings are energized in a particular sequence in cyclic manner. The rotation is incremental and precise, with each pulse causing the rotor to move by a fixed angle, and this fixed angle is said to be the step angle of the machine. Now let us start the detailed discussion from the variable reluctance stepper motor. So, the variable reluctance stepper motor works upon the principle that when a magnetic material is placed in the magnetic field, it will experience a force to align itself such that the path for the flux so created is having the minimum reluctance. It has a stator with salient poles, and the salient poles are wound with the concentric winding, and this is going to form different phases of the machine. The stator phases are excited by current pulses to establish the magnetic field. The rotor also has salient structure with projecting teeth and has no winding or the permanent magnet. The two types of variable reluctance stepper motors are the single stack stepper variable reluctance stepper motor and the multi-stack or multiple stack variable reluctance stepper motor. So now let us start with the single stack variable reluctance stepper motor. So here lies the basic constructional points of the single stack variable reluctance stepper motor. Starting with the material for stator, it is made up of silicon steel stampings. It has projecting poles, or we can say the projecting poles usually even numbered. The poles carry the concentric windings. All this I have shared on the previous slide as well. In the stator, with even number of poles, this is something which is very important. The windings on opposite poles are connected in series so that the magnetic field produced by them add each other. The windings connected in this way form different phases of the motor. Now, the stator with odd number of poles, the number of phases and poles are always equal, right? As far as the rotor of the machine is concerned, the rotor is usually made up of laminated solid silicon steel is also used instead of using the laminated structure for the rotor. The material used for stator and rotor should have highest permeability. The rotor has projecting teeth on its outer periphery and there is no winding or the permanent magnet. The number of rotor teeth and stator poles should not be equal. If they becomes equal, then motor will no longer remain a self-starting one. So, not having the rotor teeth and stator poles equal, we make the machine self-starting and it also possesses the bidirectional rotational capability. So, keep it in mind that the number of rotor teeth and number of stator poles should never be equal in case of a variable reluctance stepper motor. Now here comes the example of a 4-phase 8-pole single stack variable reluctance motor with 6 rotor poles along with the switching circuit for exciting the stator phases. So how many stator phases do you see over here? We are having 4 stator phases. 1 A dash, then we are having B dash, then we are having C dash, then we are having D dash. So the 4 phases are connected in this manner across the supply as shown over here. So this is the supply. Phase A controlled through the switch S1. Phase B energization controlled through the switch S2. Phase C is being controlled through switch S3. Phase D is being controlled through switch S4. This is basically an 8/6 variable reluctance stepper motor. Now, considering the working of the motor, under normal condition, when none of the phases are energized, rotor may take any position. For example, consider this particular figure. This is the random position of the rotor. This is the case when none of the phases are actually energized. Now let us energize phase A. Phase A, that is switch S1 is turned on and a current starts flowing in the coil of phase A. So the magnetic field so created will cause the alignment of rotor teeth 1 and 4 along with the projected poles A and A dash of the phase A, and this will provide the minimum reluctance path for the magnetic field. So a force actually acts on the rotor, and this force causes the alignment of rotor teeth as shown in figure with the phase A, with the magnetic field created by phase A, right? Now, let us see what is happening next. If you want to rotate the rotor in, say, for example, counterclockwise direction, right? If you want to rotate the rotor in counterclockwise direction, that is this particular direction, the next sequence of turning on the switch would have S2. S1 would be turned off, S2 would be turned on, right? This de-energizes phase A and energizes phase B. The stator poles B and B dash gets magnetized. It can be seen from here. Phase B is energized in this particular case. Rotor will move in a direction to occupy the minimum reluctance path by traveling the minimum angular distance, and in doing so, you just consider these two figures. This is the first figure when phase A was energized. Now phase B is energized. So the minimum rotation required by the rotor to align it into the minimum reluctance path is to align itself, to align the teeth number 2 with B and 5 with B dash projected poles of the stator phase B, right? So the rotor moves by one step angle and aligns itself with the magnetic field created by phase B. The next sequence, this will make rotor to rotate in counterclockwise direction by one step angle. What it is the same thing that I have just told you. The angle through which rotor moves for single switching operation is called the step angle, and the step angle is denoted by this formula. It is 360 divided by m dot nr. Here m is the number of stator phases and nr is the number of rotor teeth. Here in this particular case, m is equal to 4, so we are having a 4 phase stator, and nr is equal to 6, that is we are having 6 steps over the rotor. So solving with this, the step angle comes out to be 15 degree. Now when switch S2 is off and S3 is turned on, see, switch S2 is off, so B is de-energized, S3 is turned on, so that the phase C is energized now. So when S2 is off and S3 is on, the rotor again moves by 1 step angle in the counterclockwise direction. You can see it over here. Now this is the new position of the rotor. Rotor again rotated by 1 step angle in counterclockwise direction to align itself with the magnetic field created by phase C. And just like that, if you change the sequence from, if you turn off the switch S3, de-energizing phase C, and if you turn on the switch S4, energizing phase D, it will cause movement of the rotor further by 1 step angle in counterclockwise direction, so as to cause the rotation of the rotor as per the switching sequence. So in this manner, simply by changing the switching sequence, we can control the position of the rotor movement. The motor operation can be explained with the help of the following truth table. It is the same thing. Switch S1 is turned on. That particular position is assumed to be the reference position. So the angle theta is taken 0 here. Now when switch S2 is on, the rotation is by 15 degree. When S3 is on, the rotation would be further by 15 degree. When S4 is on, further rotation of 15 degree would be there. And again when we turn off S4 and S1 is turned on, the rotation of the rotor would be by further 15 degree, where 15 degree is the step angle for this particular motor. So it was about the single stack 8/6 variable reluctance stepper motor. In next class, in next lecture of the subject, we will discuss about the various modes of excitation, modes of operation of this particular motor. So depending upon the excitation of stator phases, 4 modes are possible: single phase or full step on mode, 2 phase on mode, half step mode, which is 2-1-2-1, and the micro step mode. So that's all for this particular lecture. Thank you.